My name's Ethan Donowitz. I'm a senior software engineer at Discord, and today I'll be talking about how Discord performs database upgrades at scale. So a little bit about myself. I work at Discord on the persistence infrastructure team. Our team owns all of the persistent data stores in use across Discord, mostly ScyllaDB and Postgres. I live in New York City, and my favorite color is purple. So during this presentation, I'll be covering what makes database upgrades scary, how we use something at Discord called shadow clusters to make them less scary, how we use what we call data services for traffic mirroring and read validations, what we monitor when testing a new version of our database, and how we could make this process less toilsome operationally. So imagine this. You have a new version of your distributed database. It's released with the latest and greatest features, and it promises to improve query performance by an entire order of magnitude. But your database cluster gets hundreds of thousands of queries per second and contains hundreds of terabytes of data. Your database cluster is used in many critical flows in your application, so downtime would be a pretty bad thing. So how do you verify that it's safe to upgrade to the new version, and how do you actually perform that upgrade safely? So here are some of the potential risks you could run into. There may be changes to data formats or query semantics that could result in data corruption. That could be due to a bug in the new version of the database, or because data is being returned differently by the database, which could cause your application to write bad data back. During the upgrade, a node may not be able to boot, and downtime may not be tolerable. Changes in performance in the new version of the database may affect upstream systems and users, and even small changes in performance may have pretty compounding effects depending on how latency sensitive your application is. And coordinating a complicated upgrade from an operational perspective is pretty toilsome, and it leaves a lot of room for operator error if you don't have the right tooling in place. So how can we de-risk this process? Well, maybe we can test in a staging environment, but staging doesn't quite simulate the load in a production environment. Most staging environments don't really receive much traffic at all, so that probably won't work very well. We could try writing a load testing framework, but it's pretty difficult to accurately simulate the query patterns from production. And then tailoring a framework like that to the schemas across all of the clusters would be very time consuming. For that, we need to simulate performing all of the queries we perform in production in the correct proportions and at the same load that they're being produced in production. That sounds really hard. We'd probably need to distribute this load tester across multiple hosts because executing hundreds of thousands of queries from a single process may not even be possible. Well, if that doesn't work, maybe we can try capturing production traffic and then replaying it. That's a bit closer, at least you have the correct proportions of queries, but it still requires substantial work to determine how to capture traffic, where to store it, and how to replay it. If your database cluster is receiving hundreds of thousands of queries per second, that could be a lot of data that you need to store in order to reproduce that traffic over a day or multiple days. You would still possibly need to distribute that the load generation across multiple hosts, which could be cumbersome. And there may also be privacy and compliance concerns here. So none of those ideas really sound ideal. So at Discord, we use what we call shadow clusters. So what is a shadow cluster? A shadow cluster is a mirror of a production cluster that has mostly the same data and receives all the same reads and writes. It's created from disk snapshots from production nodes in its corresponding production cluster. Production traffic, both reads and writes, is mirrored to the shadow cluster via what we call data services, which I'll talk about in a little bit. And in general, for a given upgrade, we create a shadow cluster for each of our production clusters and run tests, various tests, which I'll talk about before performing the upgrade in production for real. So setting up a shadow cluster consists of a few steps. First, we need to provision the infrastructure. So we use Terraform to provision the compute instances and the disks. As I mentioned, the disks are created from production disk snapshots, which ensures that the cluster has roughly all of the same production data, but I'll talk about this a bit more later. Then we use configuration management tools to set up the new instances. When you create a fresh compute instance, it's just going to have the fresh operating system installed with nothing else on it. So we're going to need to install ScyllaDB. We're going to need to apply the right configuration. We're going to need to install the database, the Datadog agent, things like that. And then finally, we wait for the nodes to come online and finish compactions. Basically, just wait for the cluster to reach a steady state. Compaction's finished, system resource usage levels off, and all that. So now that we have our shadow cluster set up, we're going to shift our focus to what we call data services and how we use them to perform read validations against the shadow cluster. So what's a data service? Well, it's a Rust gRPC service that sits between our Python API monolith and our databases. So typically, each RPC that we define in these services consists of a single query. So the data service receives an RPC, and that RPC will issue likely one query to the database, and then get a response, serialize it, and send it back to the client. These data services can perform query coalescing, which is if we receive multiple concurrent queries for one key, we only issue the query once. So if you basically have a bunch of RPCs sharing a single query to the database, which substantially reduces load for a very hot key. And this is much easier to deal with in caching because there's no state, and you don't have to worry about anything like cache invalidation. These data services can also implement custom arbitrary logic that might be expensive to implement in Python. So that might be data format conversion, something like, if you have a query that returns a bunch of rows and you want to filter some of them in memory because the filtering can't be done by the database, that's something we can do in the data service as well. We can also do rate limiting. So with all of this combined, the data services serve as a kind of a protective layer for our databases. So you can see here, you have the Discord client. It talks to the API monolith. And then the API monolith has a bunch of RPC clients, one for each data service. And then it talks to the data services. And then each data service talks to one ScyllaDB cluster, the production cluster. So that's the overall architecture. So another thing that data services can do is mirror traffic to a shadow cluster. They can also perform read validations, which is when we compare results from the production and shadow clusters to make sure that they're the same. So at a high level, that process looks like this. We issue a query to the production cluster, and we wait for the results. When the results are returned by the database, we pass those results into an asynchronous task that issues the same query to the shadow cluster, waits for the shadow cluster results, and then compares those results to the production results. If the comparison is successful, it emits a metric, and if it's unsuccessful, it emits a different metric. While that asynchronous task is running, we forward the results back to the requesting client, and the task finishes in the background. So this process doesn't slow down queries for actual RPCs that are incoming. Any production queries still go through as we expect. So this is what the architecture looks like with the shadow cluster involved. It looks very similar. The only main difference here is that the data service now talks to both the production ScyllaDB cluster and the shadow cluster. So now we're going to talk a little bit about read validations. So the data services issue the same query to both this production and shadow cluster, as I mentioned. These data services are written in Rust, and Rust has an asynchronous runtime called Tokyo, which makes running these asynchronous tasks very easy. Database queries are I/O bound, and Tokyo is designed to handle a very high number of concurrent I/O bound tasks. So we're able to make very efficient use of resources on the data service while we're doing this. If the results don't match, as I mentioned, a metric is emitted. And this process gives us a lot of peace of mind, right? It lets us know that the queries that we're issuing on both the production and shadow clusters are returning the same results. That's really invaluable. We're sending real production queries, we're getting real production results, and we're comparing them to make sure they match. Setting up read validations can be a little bit tricky. So because shadow clusters are created from production disk snapshots, as I mentioned, usually from the prior day, the cluster is missing about 1 day's worth of writes. So imagine you have a shadow cluster that is spun up from these disk snapshots from yesterday, and then you start mirroring writes today. It's going to be missing any data, any mutations, so any writes, any inserts, or any updates that occurred between when the snapshot, the production snapshot, was actually created and when we start mirroring writes. all of those writes in between will have been missed by the shadow cluster. So if you imagine you have some entity A that exists in the disk snapshot, and it's mutated between the creation of that snapshot and when we start to mirror write to the shadow cluster will be missing that mutation. And as a result, when we try to perform a read validation, it will fail. Well, how do we solve this? So all of the IDs, most of the IDs we use at Discord are snowflakes. So a snowflake is a unique 64-bit integer that contains an embedded timestamp that reflects the time that the snowflake was created. And this gives them the property that snowflakes monotonically increase over time as you generate them. And this is very useful because it gives us the property that if entity A is older than entity B, A's ID will be quantitatively less than B's ID. And we use a service to generate these IDs to ensure that the IDs are unique. So we use this property in read validations to prevent false positive mismatches. So once we've got a shadow cluster stood up and we start mirroring 100% of writes from production, we generate a new snowflake and set it as the cutoff ID in the data service. And when the data service receives a read, it looks at that ID and it only performs a read validation if the ID in the query is greater than the configured cutoff ID. And this effectively is saying only perform read validations on entities that were created after we generated that cutoff ID snowflake. And this ensures that we're only performing read validations against records that were created after the shadow cluster began receiving writes from production. In practice, this means that the more time the shadow cluster is up and receiving traffic, the more read validations it can perform, because more and more of the data have been created after that cutoff point. So at a high level, the shadow cluster setup process looks something like this. We provision all the infrastructure. We slowly start mirroring reads and writes to the shadow cluster, ramping up to 100%, keeping an eye on both the cluster's health and also the data service's health. Once 100% of writes are being mirrored to the shadow cluster, we generate that new snowflake for the cutoff ID, and we set it on the data service. And then finally, we can configure the percentage of reads that actually should be validated, usually anywhere from 1 to 100%. So higher throughput services or services that return very large result sets may require a lower percentage, simply because checking big result sets for equality may be really resource intensive. There's only a set amount of CPU on these data services, and we need to be careful to make sure that we're not interfering with actual production traffic. Now that we have the shadow cluster set up and the data service is getting all of the reads and writes, and we're performing read validations, we can actually perform the upgrade on the shadow cluster to test it. So we perform the upgrade on a rolling basis, one node at a time. Our clusters run with a replication factor of 3 and consistency level quorum. So one node going down does not result in downtime. So a replication factor of 3 means that each row is present, it's replicated across 3 different nodes in the cluster. And the consistency level quorum means that when the database cluster receives a query, 2 nodes out of 3 are required to respond to the query. And this helps to protect the consistency of the read. So taking one node offline is okay because we have the guarantee that all the data on that node is reflected across other nodes in the cluster. If we took 2 nodes offline, then we could run into trouble because then certain queries for certain keys may not actually be able to meet quorum at that point. So that's why we do the upgrade on a rolling basis. We have to do one node at a time. So at a high level, upgrading the node just looks like swapping the binary in for the new version. This might be upgrading the package via the package manager in the operating system, downloading the binary from another source and putting it in the correct install location. Then we have to update any configuration that might need to be updated across the versions. So this could look like adding new configuration options or removing them, removing ones that are old. And then finally, we drain the node, which means cease traffic to it, and then restart the node, where when it's restarted, we are using the upgraded binary. So this upgrade process is automated generally via a combination of scripts and configuration management tools. We monitor the shadow cluster very closely while the upgrade takes place to ensure it remains healthy. We want to see that there aren't a bunch of failed reads, that latency is not spiking at other nodes, things like that. It's also a very useful exercise to perform the upgrade exactly as it would be performed in production to keep the testing process as close to real life as possible. You want to make sure that when you're performing the upgrade, your upgrade process, your testing process looks exactly the way it would look in production to get the most accurate test results as possible. It's also just useful as an operator to practice performing this kind of operation in a production-like environment as preparation for the real deal, just for the experience. So one of the things we monitor after the upgrade is finished is query latency, query performance. Our data services have per query latency metrics, which is very useful. We're able to compare the per query latencies between the production and shadow clusters to look for regressions or improvements. And we're actually able in Datadog to chart the percent change in latency between the shadow and production clusters per query. If we encounter a latency regression, which is pretty rare, we look at the context. So where in the application is the query used? Some endpoints are more latency sensitive than others, and sometimes we can just tolerate a latency regression. What is the absolute latency of the query? So, if you have a 50% regression in a query with sub-millisecond latency, then that's a pretty negligible, regression, right? If you have a query that takes 100 microseconds and now it's 150 microseconds, that probably doesn't matter. That's still well under a millisecond. And sometimes we just need to wait for the cache to warm. Our production nodes are running for long periods of time. The cache is generally very warm all the time. And if you're creating these new shadow clusters from scratch and you're not letting that cache warm up, there may be more disk reads happening. And the keys in the cache may not reflect the actual distribution of the hottest keys in your workload. As I mentioned, latency regressions are very rare. And when we encounter them, oftentimes performance can just be improved just by tuning settings. We also monitor read validations very closely. So we watch that metric I mentioned that counts read validation mismatches. Occasionally, there are some false positives due to the differences in the way that reads and writes are interleaved and applied on the production and shadow clusters. So to account for this, we actually retry these read validations a fixed number of times to check to see if the data converges. And if the results never converge, then that starts to suggest a problem. And if we do encounter a read mismatch, we can actually just inspect the mismatch data to see what's different. And usually that tells us what's going on. So in practice, I personally haven't seen, I don't think, any read validations mismatches that were due to a problem in the new version. We tend to just run into a few false positives due to things like failed requests and stuff like that. In addition to that, we just perform a bunch of general testing. So this looks like, knocking over a node to simulate a host failure, which is something we occasionally encounter in production, performing a repair, which is a maintenance process that synchronizes data across the nodes in a ScyllaDB cluster to help maintain consistency. We also perform a schema migration to make sure that that looks okay. We look closely at our metrics dashboards to make sure that metrics are not broken in the new version, that sometimes metrics are added in new versions, or metrics we were relying on might be removed, or they might just be renames, things like that. And finally, we perform a backup. So to wrap up, Shadow Cluster has been a really invaluable tool whenever we need to test a risky production operation like an upgrade. It gives us an opportunity to practice running these operations before actually performing them in production in an environment that looks almost exactly like a production environment, which is just about the best test that you can get for something like this. And our data services serve as a really convenient place for us to implement traffic mirroring and read validations. Looking forward, we're hoping to automate more of this process using something that we're calling the ScyllaDB control plane that we're building from scratch. So right now, shadow cluster testing is a very manual process. We have scripts to help us, but they tend to be pretty brittle. So we're currently investing time in building a control plane to manage our ScyllaDB infrastructure. It'll eventually allow us to hopefully automate most of the shadow cluster creation process, short of actually using Terraform to provision the infrastructure. It'll help us to update settings across the nodes in a cluster. It'll help us to install new versions. We can restart nodes. We can do a rolling restart of the whole cluster. The idea is that it will help us with some small one-off operations like restarting a single node or running some kind of CQL statement on one of the nodes. to coordinating even more complicated workflows across the whole cluster, like upgrading a cluster one node at a time. And that's it. Thank you. I really appreciate your time. You can find me on GitHub and LinkedIn here. Yeah, thank you.